We were learning about arithmetic sequences, and we saw a few examples of arithmetic sequences, and we also saw what are not arithmetic sequences. We were solving a few problems regarding that. So I came across this very specific problem in a very popular book. The name of the book rhymes with Moriarty. Uh, the, the the answer given in the book. So this was the sequence. First of all, a squared, a cube, a to the power 4, and this goes on forever. So we have to guess whether it's an arithmetic sequence or not. So this was a problem given, and the reason I am taking a full video for this problem is because the way they have given the answer is not very satisfactory to me, and according to me it needs a little bit more attention than we have given it. So at first glance, uh, we just see that each of the next term is obtained by multiplying the previous term by a. So a times a is a squared, and a squared times a will give you a squared times a would give you a cube, and this times a. So each of the term, it doesn't look like an arithmetic progression at first glance, but let us use the same technique that we use to determine whether it's an arithmetic sequence or not, and then just decide. The technique we used was we took a term at random, so say this one, and we subtracted the previous term from it, and we saw what the difference was, and we saw what this difference was, and we took another two terms, this one and this one, for example, of course, and we subtracted these two and saw the difference, and if the difference had been equal to this, say the difference we obtained before, we concluded that it's an arithmetic sequence. So we know the general pattern of the sequence. So for us to conclude that it's arithmetic sequence actually requires us to do this for each and every term, because that's the requirement for the sequence, but we don't do it. We have the general idea, so we take any two terms, we compare it, and we just say that it's a part of a arithmetic sequence. So for this to be an in arithmetic progression, the difference of these two terms should have been equal to the difference of these two terms, right? So a squared minus a should have been equal to a cubed minus a squared. So let us just think about this for a while and see where it leads us. If the way again I'm stressing on this because this might be a little bit too advanced for this level, but it's an interesting exercise for you. The way I arrived at this is I am just saying that for this to have been an arithmetic sequence, the difference of consecutive terms should have been the same, and hence I wrote this equality. So pause the video if you don't understand this this form of logic, and just ponder upon it, and then play the video, and you'll be fine. So now that we have this equation at hand, let us manipulate this and play with it. Uh, can I first of all, well, I'm assuming of course that a is a real number. So a is a real number. So a is any real number. So real numbers have the distributive property, and you can of course take an a common from the first left hand side of the equation, and this would give you a minus 1. So this the way to verify it is you get from here to here by multiplying, and this side we have an a squared common, and the thing that's left inside is a minus 1 again. So now we might be very tempted to cancel out the a minus 1s and a and see what happens, but you can only cancel out these a minus 1s from both the sides The reason for cancelling out is you divide both sides by a minus 1, and then we say that we cancel out, but we actually divide both the sides by a minus 1, and hence a minus 1 to be able to be divided by a for something to be able to be divided by a minus 1, a minus 1 should not have been equal to 0. That's the condition we have. You cannot divide anything by 0, so if and only if a minus 1 is not equal to 0, we'd be able to perform this division, and we could say that this equality is the same as this equality, a is equal to a squared. Fine. So now we have this condition at hand, a is not equal to 1, and this might hint at what I am trying to get at here, but let us wait for a while. Now a is equal to a squared. Again we can cancel out a's and we can get a conclusion, but cancelling out a means you are dividing both sides of the equation by a, and hence a is not equal to 0 because you are dividing by a. So this you'll have to remember, and you can then divide by a, and you can say that a is equal to 1 is equal to a, and this cannot be true because a minus 1 is not equal to 0. So we have arrived at, for no values, so this cannot be true, which means what? For no values of a, the sequence is arithmetic. For no values of a, can this equation be satisfied, which is the same as saying for no values of a, the sequence is arithmetic. And for no values of a, let me underline this no, because we have already disregarded two values of a, and we have made this conclusion for other remaining values of a. So already we have that a minus 1 is not equal to 0, which means what? A is not equal to 1, and a is not equal to 0. So two values of a are very shady. And now I could have done this at the starting of the video. I could have just substituted a is equal to 0 and 1 and looked at the sequence, but I think this was more fun. So now if I look at the sequence again, I found out what the problematic case were. So for a equal to 1, what happens? What if a had been 1? The sequence would give us 1, 1, 1 cube is 1, 1 to the power 4 is 1. So this is my sequence. And for a equal to 0, what has happened? 0, 0, 0, 0. So now, do you see what the problem is? If I had concluded this is not an arithmetic sequence for all real numbers, then my statement would have been false, because this actually is an arithmetic sequence. The common difference is 0 in this case. It's a constant sequence. Also, this is an arithmetic sequence. So I just wanted to clarify that. Hope this is not too tough to follow. You can rewatch the video multiple times, because this form of logical arguments might not be usually done in your school, and you might not be used to this, but this is quite interesting, the way we manipulate these equations to arrive at actually we could have guessed this, but we just arrived at it mathematically.